Hey guys, welcome back. We got Arrhenius and Catalysts. All right, so first we're going to dive into Arrhenius and the Arrhenius equation. So this is Savante Arrhenius. Back in 1889. All right, so that's quite a while ago. All right, he said temperature affects the rate at which reactions occur. The rate at which reactions occur. Okay, and it's in the rate constant K. So it's in that lowercase k. All right. And so our rate constant K all right, he came up with an equation how this works. All right. And with experiment and graphing and all that, he came up with the Arrhenius equation, which is, it's got this thing A, which is a pre-exponential, E, right, to negative EA divided by R and T. All right, let's define everything. A is our frequency factor. All right, so this represents collision frequency and the collisions with the correct orientation. All right. So that means if A is large, right, then the orientation requirement is probably not critical. EA, activation energy, all right, and that's going to be in kilojoules per mole. R, of course, 8.3145 joules per mole Kelvin, gas constant. And then T is our temperature. In Kelvin. All right. And so let's dive into this A. All right. And so A can be broken up into two smaller letters. We'll do P and Z. P is the orientation probability. It goes from 0 to 1. So if it's 0, it's towards 0, it's strict. And 1 is any orientation. So, for example, hydrogen and oxygen, H2 and O2, no matter what, their collision's pretty much going to be good. And so it's closer to 1 for P. Big biological molecules, sometimes they're way more strict. And Z is collision frequency. Right? And this is typically large, right, at ambient temperatures. Right? Now, if we were to do this, all right, so what happens here, this Arrhenius equation, it's a good equation. If you take the natural log of K, all right, you would take the natural log of A, then you get minus EA over RT. Well, separating this out a little bit and rearranging it, all right, you can get the natural log K right, equals negative EA over R times 1 over T plus natural log of A. And hopefully, if you look at that, like, why would we do that? Hopefully, that's what you see. Y equals mx plus b there. All right? And so what we can do, if we can make this a line, we can use the 2-point form, where you have two different temperatures and two different rate constants, and you'll get the natural log of, we'll do it this way. I'll do purple K, K1, and, well, I'm going to do those different colors. K and K equals EA over R and we got two T's. So now, very important, T1 and K1 go together. So K1 and T1 are here. And K2, oh, no, I got it backwards. Do it this way. So that is one, there's other ways to do this, right? You can have it negative and flipped and all sorts of, however you derive it. Okay, now, it's important that the K's are in the natural log. K1 over K2, EA over R, 1 over T2 minus 1 over T1. Right, that's the 2-point form, all right, of the Arrhenius equation. So now, as long I can solve for, what can we solve for with this? We can solve for the activation energy. We can solve for a rate constant at a different temperature. We can solve for, if I have two different rate constants, I can solve for a temperature. So I have 1, 2, 3, 4, 5 variables, but ultimately only 1, 2, 3 things. A rate constant, activation energy, or a temperature. Doesn't matter which one. All right, so that's the form of the Arrhenius equation. Now, with this, we have the next term of catalyst. And I want to put in what a catalyst is. So let's talk about catalyst. So a catalyst is a substance that increases the rate of the reaction all right, so we increase the rate of reaction, all right, and it does so by providing a new pathway or mechanism with lower activation energy. So it's a whole new reaction. So it's the same reactants, same products, different way to do it. All right. So catalysts can be, they can be heterogeneous, right? Which is different phase. Right? Think about a catalytic converter, a car or automobile catalytic converter. It's either palladium or platinum or some proprietary mixture of precious metal. That gas, exhaust gas goes, and that solid catalytic converter changes the gases into something that's less harmful for the atmosphere. Right? So that would be a catalytic converter, would be a heterogeneous catalyst because it's in a different phase. Now, the other way a catalyst can be is homogeneous. And you're probably already ahead of me. It's in the same phase. So we're in a single phase. With the reaction. That's typically liquid. Especially for what we want. But it can be gases as well, all right? Gases can do it as well, all right? And an example would be enzymes. All right? So enzymes are an example of a aqueous catalyst in the body that speed up reactions a lot. And so what do we mean by this? So let's take a little picture here with catalyst. We got the y-axis, and this would be energy. And then I have the x-axis, will just be the reaction. Right? Reaction progress. All right, and so what we have is a reaction. Let's just say we have A plus B going to C and D, right? All right, I'm going to have my reactants here. Actually, I'm going to lower them a little bit to exaggerate. And we're on my products over here. All right, so there's a couple things that are still true. That's still delta H, right? The enthalpy of the reaction. All right? If we just do our normal reaction, something like that, right? Right? That's our uncatalyzed reaction. I have right here the transition state. And this is my activation energy for my uncatalyzed pathway. All right. If I were to add a catalyst, all right, a catalyst would change how we do this. So a catalyst might have something like this, where you have a lower first activation, but now you get a second step, and then it comes down to products. So you would have here EA1, and then we'd have another EA2. So we made it 2 steps, right? And then in here, we now have a new intermediate, right? Okay, with 2 more new transition states, all right? Okay, but if you look, this is our catalyzed pathway. So what does this all mean? That means that it's EA1 is smaller than EA2. So that typically means we're going to have a faster reaction. All right. And now, instead of making like a one-step reaction, we made it step 1 and now step 2. So we made it 2 steps, right, with smaller EA. And it's just like, think of it like a roller coaster here. Once you go to the top, the first peak that's high, you got enough energy to come down and go through the second peak, usually. Not always, but usually. All right? And so that would be an example of what a catalyst does with activation energy. Now, next up will be mechanisms, and we'll talk about actually how this all works. So if you have any questions, feel free to reach out. Otherwise, we'll see you next time.